Hello everyone, you are welcome to another video session of Python for All. In this video, I will talk about array computing. Before we get started, let's look at what an array is. An array is a structured data that stores data in a contiguous block of memory, in other words, in a sequential block of memory or pattern. This allows for efficient access to the data, as the elements of the array can be accessed by their index. Arrays can be one-dimensional, two-dimensional, or three-dimensional. More specifically, in Python, for we to be able to use our array, we need to use the library known as NumPy. So to show an example here, we will import NumPy as NP. So the as NP is simply importing NumPy using an alias or a short form, which is NP. Now, to get an array in Python, once you have imported NumPy as NP, you simply call the function np.array and then pass in the array. You can see the 1D array we have passed into the function np.array a list. Likewise, in the 2D array, we have passed into the function a list of lists. So we will run this cell and see the output of the row. So we want to print out the 1D array and also print out the 2D array. If I run this cell, you see the 1D array prints the one-dimensional array and the 2D array prints the 2D array. We can likewise find the shape of this array. In other words, we can get the dimension of this array by simply calling 1D.shape or 2D.shape. In the same vein, you can access elements of this array by using the square bracket and the respective index. For example, the 1D array, accessing the 1D array, okay, and getting the first element of that array is simply calling 1D in square bracket 0, since Python indexing starts from 0. Running this cell gives us the first element of the 1D array, which is 1. But for 2D arrays, we simply access the element of those 2D arrays using just a single square bracket, and then the indices of that array is placed inside the square bracket. Unlike in the case of list, we access the list of lists by using two separate square brackets, which you can as well do here, but because NumPy has what we call fancy indexing, it's preferably accessed using just one single square bracket, as you can see here. Here, I want to access the element on the first on the second row, because one means second, on the second row and the third column. Running this cell gives us 8. Let's look at it. Go back to the 2D. This is the first row, which is 0, the second row, which is 1, the first column 0, second column 1, third column 2, and that element is what? 8, which is correct. Likewise, if I call 1, 1 and run this array, what does it give me? It gives me 4, which is on what? On the second row and second column. If we call 0, index 0, and index this to be 2, it means it gives us the first row and the third column. What's the element of the first row and third column? It is 3. Now, array indexing in Python. Array indexing in Python is a process of accessing elements of an array. NumPy arrays can be indexed using integers, which I've just seen, using slices, which we are going to see very shortly, and using Boolean mask. In the special case of Boolean mask, you'll see that when you are dealing with image processing and trying to access the pixel values in every image array using Boolean mask, or also trying to create a mask. Now, to convert a list R to an array, we use the function np.array. Also, we can use the function np.asArray. To create a new array of length L filled with zeros, we simply call np.zeros. Okay, we also have np.ones, create an array of ones for a particular length of n. A similar function, np.zeros like, can also be used, but in this case, we do not pass in the dimension or the length of the array. We simply pass in another array, which it creates zeros based on the dimension of that array that is being passed in. Now, when we want an array to have n element of uniformly distributed values in an interval of p and q, the NumPy function to use is a linspace. So the linspace creates an evenly distributed array between two intervals for the specified number of elements. That you can see here, np.linspace pq, and then the number of linearly spaced element or vectors specified there. An array can be accessed by square brackets as for list, just as A into square bracket of I. Slices also work for list. For example, you are slicing from the second element until the last element. What happens is that in the case of list, it picks out all the elements except the first and the last. In other words, the first element is not inclusive and the last element is also left behind. But contrary to list, a slicing from 1 until -1 is not a copy of the data in A. In the case of an array, when you slice, a copy is created. In other words, what it means is that because we mentioned earlier that arrays are contiguous block of elements stored in memory, elements stored in contiguous block of memory. So when you slice an array and you modify the slice array, the original array also gets modified. So here we have b is equal to a slice of a, and then if you can easily modify the third element in b to be zero point 0.1. Now, a slice beginning from I to j with a step of s simply has a starting index of I, a stepping of x indices at the time up till not including j. So in the case of array, it begins with the I, okay, following the stepping until but not including j. Now, omitting I implies I is 0, and also omitting j implies that j is equal to n, okay, the number of elements in the array. For example, if I slice a from 0 until -1, which means until the last element with a step of 2, it picks up every two elements but not including the last element. While if I slice with double colon and 4, it picks every four element of the whole array, meaning that I is equal to 0 and j is equal to the total number of elements. Also, when importing NumPy, do not do from NumPy import asterisk. This is called wildcard import. What it does is that it pollutes your namespace with all the functions in NumPy. Simply, for example, if you want to write this function f of x equals sine h of x minus 1 sine x wt, simply from NumPy import shine and sine. Then you can proceed to define the function, the respective input, and then return the value from the function, which is shine x minus 1 multiplied by sine w times t. Okay, let's demonstrate by creating a simple array. Then here we'll talk about the shape of the array, the size of the array, and the type of the array. So here I have array A equals np.array, and I have my array right in here, which is a two-dimensional array. And then I specify the D type to be float 32. Now, if I will print the A, I will also print the shape of A, print the size and the D type. Here, if you print A, you can see that A is printed, unlike the array we passed in were just integers. Because we specified the D type to be float 32, you can see it comes with the floating point, 1 point, 2 point, and so on and so forth. And then the shape of the array is 3 by 4, which means 3 rows by 4 columns. And when you do a dot size, it gives you the total number of elements in that array. And the D type, it tells you it is float 32. Let's move on to vectorization and NumPy. Vectorization is a technique that can be used to improve the performance of numeric operations on NumPy arrays. It involves performing mathematical operations on the entire array rather than individual elements. There are two main ways to vectorize NumPy codes. The first is using the NumPy functions. NumPy provides a number of functions that are specifically designed for vectorized operations, for example, the np.sum that can be used to sum the elements of an array. The next or the second is using the NumPy unfunc. The unfunc is also known as the universal function and is a special type of function that can be vectorized over arrays. They are typically faster than NumPy functions for vectorized operations. Now, let's look at codes without vectorization. Here I have a list and I want to find the square of that list. So I have num, which is a list, and num squared, an empty list, and then I run through a loop and append the square of every element in num to the num squared. Let's print num squared and the type of num squared. If we running this cell gives us num squared, of course, and it tells us that it is a list. That's what the type tells us, class, and it is a list. Now, let's run similar code using vectorization. Here, to use vectorization, we first of all import numpy as np. Then we create the array. Here we have num equals np.array of we pass in the list. Now it is now an array. By default, it gives us in 64. So next, to find the square of all the numbers, we simply call np.square. Np has a function square and then pass in the number. Let's print the num squared and then print the type and we see the result we have. Here it gives us same result, and then we have the array num squared, and then the class is what np.nd array, which means it's a numpy array. Now, of these two implementations, let's use the another module known as time it to check the time of execution of these two code and see which one is faster. So let's go back to without vectorization. To do that, we simply import time it from time it, and then of course we have our num and then num square empty. Then we write the loop for n in num. We begin this magic symbol, percentage symbol, time it minus n, and we want to run execute this code for 100,000 times, and then we pass in same function that we have had written earlier, num square dot append n squared. So we are simply looking at individual elements and squaring them and then appending them to the empty list num squared. If we run again, you see first it takes 302 nanoseconds to run the first loop because we are looping 6 times. So in total, if you sum this up, we're an average of about 1,400 nanoseconds. Now let's look at the one code done with vectorization. To do that, we simply import numpy as np, and then we have num equals np.array, passing the array. And here there is no explicit loop. We just simply call time it again, and then run it for 100,000 times, and then passing num squared equals same like we have written earlier. Okay, running this gives us 417 nanoseconds. So you can see that the vectorized one is way much faster than the unvectorized form of the code. Now, let's see what we have with list comprehension. Okay, with list comprehension, we simply have the same num and then we just pass in the function list comprehension num squared to time it. If we run this again, what we have, it takes 1.55 milliseconds, even way much more faster than numpy array. Let me mention here that in some instances you have the list comprehension running faster than the vectorized implementation. It may run faster, but when we begin to handle much more larger data, the least comprehension falls short of performance as compared to the vectorized form. So in most cases, it's often advisable to vectorize your code if possible so as to gain this performance and efficiency as compared to the unvectorized form. With this, we have come to the end of this video. If you have any question, please leave it in the comment section. I will leave a link to the download of this notebook in the description box. Like this video, share this video, subscribe to my channel if you have not done so, and do not forget to click the notification bell to get notified of my new upload. Until then, I will see you in my next video.